So, earlier lectures we have seen some examples where we have tried to illustrate some structural design constructs by using instantiation of gates. So, in the present lecture we shall first see what are the various types of gates that are available as part of the Verilog language, which you can directly use and instantiate in our design. So, this is the title of our lecture, and we start with a discussion on predefined logic gates in Verilog. So, we have already seen some of these gates AND, OR, NOT, NAND, NOR, XOR. Verilog provides predefined logic gates, as I said, and we have also talked about earlier that in Verilog we support 4 logic values, states 0, 1, undefined and high impedance. Now, when you talk about gates, for example, I use an AND gate. So, the inputs of the AND gates are coming from say 2 other hardware blocks. Let us call this T1, let us call this T2. Now, this T1 and T2, they will be belonging to this set 0, 1, x or z. So, now when I say that this is an AND gate, I will also have to define what will be the behavior of this AND gate. If some arbitrary input combinations are coming on T1 and T2, what should be the value of f? Okay, this actually follows from intuition. Let us see. Let us look at an AND gate. Okay, from the definition of an AND gate, 0 and 0 is 0. Well, if one of the input is 0, other is 1, it is also 0. When both the inputs are 1, then it is 1. Now, let us look at the behavior with x, one of the input at x and the other input is 0 or 1. So, if one input is x and the other is 1, for an AND operation you cannot say what is the output, but if the one input is 0, then you can definitely say that the output will be 0. Similarly, for the high impedance state, some other things. So, if one of them is 1, other is the high impedance state, then the output can be in an indeterminate level, I call it x, and if one is z, other is x, output is also x. So, for OR operation it is again similar, 0 0 is 0, 0 1 is 1, 1 1 is 1, and for do not care if one of the input is 1, then the output is definitely 1, but for 0 you cannot say. So, for these cases again x. For XOR similarly, 0 0 is 0, 0 1 is 1, 1 1 is 0, and for other cases you really cannot say. For XOR function, if one of the input is x or z, the output will be undefined. So, for all the gates you can define the behavior in terms of the 4 valued logic 0 1 x z like this. Now, talking about the list of gates, this is the complete list. The basic gates are these AND, NAND, OR, NOR, XOR, XNOR, NOT. There are buffers and there are some couple of more NOT gates. So, I will explain this. Okay, for the normal AND, NAND, OR, NOR, XOR or XNOR, the number of inputs can be arbitrarily. Like for example, for AND, I can write an instantiation AND, gate is G, and so I can write like this A, B, C, D, E, F. This will mean that the first variable that I am using here, this will be my gate output, and all the remaining variable, there are 5 here, these will be my inputs. So, actually I am defining a 5 input AND gate, where A is the output and B, C, D, E and F are the inputs. So, in this way it depends on how many variables I am using in the parameter. So, the number of inputs of the gate will be defined accordingly, right. So, there is a flexibility. NOT is simple, NOT will have a single input and a single output. So, the input is in, output is out. Come to buff, buff is just a buffer. Sometimes you need to means isolate signals. This out equal to in, the logic value does not change, but the signal values are restored. Okay. This is a buffer. Now, there are some tri-state version of buffers and NOT. Buff if 1, let us say, let us see this first. Buff if 1 is something like this. It is a buffer which is selected by a control signal like this. So, this is CTRL, this is in, this is out. So, the behavior is, if your control is 1, then out will be equal to in. If control is 0, then output will be tri-state. It will be in the high impedance state, right. This is your buff if 1, this gate. Similarly, you have another gate called buff if 0. Buff if 0 is similar, the only difference is that the polarity of the control is different, there is a negation here. So, it is just the reverse, if control equal to 0, then out equal to in, if control equal to 1, out equal to high impedance state. This is buff if 0. Similarly, there are equivalent versions for NOTs. NOTs are very similar, I am just showing the diagram, I am not writing the expression. Instead of the buffer, this will be NOT. So, the output will be in bar and there will be a control. This is NOT if 1 and there is another version NOT with the control inverse. This is NOT if 0. So, this kind of tri-state control gates are also available if you want to use it in a design, right. Okay. So, when you are instantiating these kind of primary gates or primitive gates, there are some restrictions you need to remember. Like for example, here the outputs, the first argument or the parameter is the output. The output port must always be connected to a net, it cannot be connected to a register. Okay. So, an output signal in a module is a wire by default. So, you can directly use it if you want, right. Now, the input ports of the gate, like for example, this in 1 and in 2, these can be anything, they can be connected to either nets or register type variables. This I have already said that they have a single output, but can have any number of inputs, the basic gates except NOT and buffer. Well, and you have seen in the examples earlier that when you instantiate a gate, you can specify an optional delay. Like suppose you specify an AND, you can write AND #5 G1 F A B like this. Now, this delay is again only for simulation purpose. For synthesis purpose, this delay does not make any sense, right, because it is ultimately the hardware AND gate, how fast or how slow it is, that will determine the delay. So, as a designer, I have no idea what the delay will be, how many picoseconds or how many nanoseconds, right. Okay. So, this optional delay, this is used only for simulation, and the logic synthesis tool will ignore these delays. So, let us take an example which shows these delays. So, here we have a structural representation. Well, ignore the first line for the time being, I will explain this, what does this mean. This is an exclusive OR function realization using NAND gates, NAND and NOR gates. So, using 4 gates I can implement this exclusive NOR. Here there are 3 wires T1, T2 and T3. So, we have used this M1 is an AND, M2 is an AND, M3 AND, M4 is. Here we have all specified delay as 5, as I said. These will be used only for simulation purposes. Okay. Now, the first line timescale actually tells you what these numbers 5 mean. You see, roughly speaking, the first number here 10 nanosecond, this gives you the basic unit of time. So, when I write 5, it will actually mean 50 nanoseconds, and 1 nanosecond will be the precision of simulation. So, these are explained here in some detail. So, when you use the timescale directive, you can specify these 2 times. Now, why you need this? You need this for simulation purposes, that is the first thing. Now with respect to some module, you may have to specify some delay values, but for some other module the delay value may be different. So, it is always good to have this kind of a declaration, timescale declaration at the beginning of every module. So, if the timescale values are different from one module to the other, you can have different declarations like that. So, the syntax of the timescale command or directive is this: reverse quote timescale, you specify a reference time unit slash time precision. The reference time unit is actually used to specify the unit of measurement of time, as I had said. So, whatever here you specify 5, this 10 nanosecond is the unit, 5 into 10, right. And time precision, the second one, here in case we mentioned 1 nanosecond, it specifies the precision with which we round off the delays during simulation. That means, how accurate the simulation is. The simulation will be accurate up to 1 nanosecond. Okay. That is why we have given here 1 nanosecond. And for these times, the valid values you can give only 100 and 10, 10 and 100, nothing. You cannot write 2, 3, 5 here. These values can be 1, 10 and 100 only. And these units can be of course different. This, as I said, this was the time scale we gave in that example. So, when you write #5, it means a delay of 50 nanosecond. Now, instead of nanosecond, I can use other units also. I can use S meaning second, ms millisecond, then I can write US microsecond, PS picosecond or FS femtosecond. This can be specified. But again, these are all for simulation. This has nothing to do with the actual delay of the circuits. Okay? These are just very rough estimates which the designer has given for the purpose of simulation. Okay. Now, the question comes how to specify connectivity when you are instantiating a module within another module. Like what I mean is that, suppose I have a module, this is M1 and I have another module M2, and I am instantiating this module M2 inside here. So, M2 had some input signals, M2 had some output signals. So, here also the same input and output signals will be there. So, I will have to suitably connect this input and output signal from the other means hardware components that are there in M1, okay, so that this instantiation will work in a proper way, fine. So, there are two ways to specify this connectivity, how these input and output lines are connected. The first is called positional association, where the parameters of the modules that is being instantiated are listed in the same order as in the original module description. So, in the original module description, let us say we are defining a full adder. So, if it was sum carry A, B, C, then when you are instantiating, we have to specify in the same order sum carry A, B, C. So, we cannot change the order. Okay. But there is an alternate method called explicit association, where we can change the order, we can specify the parameters in an arbitrary order. Well, we shall see how. I mean, arbitrary order, the advantage is that here the chance of error is less, because suppose when you wrote the module for the full adder, you gave the first two parameters as sum and carry, but when you are instantiating, by mistake you have written carry and sum. So, in simulation you will see that result is not coming correctly. So, you will have to find out where the error is there, you have to debug it. But if you use this explicit association, then this kind of error, the chance of occurring will be much less. We shall see how we can use this. Okay. So, we shall be explaining with an example. First, positional association. So, we take a simple example. Let us say we have an example, some module, name is example, and there are 7 parameters A, B, C, D, E, F, Y. So, Y is the output and A, B, C, D, F are the input. Now, inside a test bench is also a module. So, we are instantiating this example, we are calling it DOT, and these are the variable names we are giving. There are total 7 parameters, we are giving x1, x2, x3, x4, x5, x6 out, but we are specifying them in the same order. The first 6 inputs we are connecting x1, x2, x3, x4, x5, x6, these we are applying, and the last one is the output, that is out, and out we will be observing, out we are printing monitor, right. This is positional association, the same order in which we have defined, the same order we will be using in the instantiation. But in the other one, explicit association, what you do is something like this. In the original example, it was A, B, C, D, E, F. So, the output was last. Suppose when I instantiate, I want output to be coming first. So, what I wrote here, here with respect to this module, the output has to be connected to out. I write dot out, now within bracket the variable name of the original module description, which is y, which means y is being connecting to out. Similarly, I write dot x1 within bracket A, that means x1 is connecting to A, then x2 is connecting to B. You see here, although we have to write more, but we can clearly see that which variable is getting connected to which parameter of the module that you are instantiating, and these can be put in any order, not necessarily A, B, C, D, E, F. I can put F first, then D, then A, then C. Okay. So, the order is also not important here, I can put in any order. This is one way to specify the parameters in instantiation. Now, some of the hardware modeling issues, well, actually when you use the assignment statements, various kind of assignment statements we have seen. We have seen the assign statement, we have seen the equal and the less than equal. Now, depending on the type of assignment statement you are using, the value that is computed will be assigned to either a net type variable, typically a var, or a reg type variable, which can be ultimately be a flip flop or a latch. A flip flop is nothing but an edge triggered storage cell, where data will get stored whenever a clock edge comes, and latch is level triggered whenever some enable signal is activated. Now, a variable in Verilog, as I have said, can be either net or register. A net during synthesis will always map to a wire. This is a matter of fact. Similarly, a register which you declare in Verilog, this will map either to a wire or to a storage cell, depending on how we have written the Verilog code. So, we shall be seeing some examples later. So, we shall see this distinction. Sometimes a register can be mapped to a wire, sometimes it can map to a storage cell. Let us see some examples. This is a module where there are 5 ports, ABC are the inputs, F1, F2 are the outputs. So, ABC I am also declared them as wires. This F1, F2, because they are appearing on the left hand side of the always, I am declaring them as reg. Well, here I am not using a clock. Here I am writing always at the rate A or B or C. What this statement means is that you execute the always block whenever either of A or B or C, these signals are changing their state. So, whenever one or more of the signals are changing, execute the always block. The meaning is this. Okay. So, here F1 will be doing a NAND and F2 will be doing an XOR with F1 and this. Now, here you see the first one will be generating a NAND, next one will be generating an XOR, it will be like this. First gate will be a NAND, where the inputs will be A and B and the output will be F1. Second one will be exclusive OR gate, where one of the input will be F1 and the other input will be C and the output will be F2. So, this will be a combinational circuit which will be generated, and for F1 this will also be a wire, this F1 will also be a wire. There is no need for any storage cell here. So, here although we have declared F1 F2 as reg, both F1 and F2 will not require any storage cell, either flip flop or latch. Let us take another example where we have changed this little bit, F2 equal to F1 XOR F2 and this. So, what does this say? Similar declaration, but F1 is fine, for F1 there is no problem, F1 equal to NAND of AB. So, let us try to just also show this what is happening. So, we are saying AB, this is F1, but for the other one I am writing F2 equal to F1 XOR F2. So, what does this mean? What I am saying is that there is an XOR. So, one of the input is F1, the output is F2, and we are saying that this output is as if the second input, right. So, but you see this kind of a design is normally not recommended. What will happen here is that, so if you do this kind of a design, for F2 a storage cell will be generated, but for F1 no need, F1 is a simple wire. So, what will happen is that for F2 here there will be a latch generated. So, the value of F2 will be stored here and the stored value will be coming here, and this latch will be enabled whenever either A or B or C is changing. This will be how the hardware will be implemented, right. This is the meaning. So, here F2 is appearing both on the left hand side and the right hand side, that is why a storage cell will be generated. So, let us take another example. This is actually the example of a latch, where there are 3 ports: data, load and D out. So, what you are writing? Input data and load are the input, D out is the output, and T is a temporary wire T. We are saying always whenever load or data changes, begin if load is 0, load 0 active, then data will go to T and D out will be not of T. See here this thing I will explain in more detail later, just one first look of this. In this if statement there can also be a else, if then else. We have specified if load is 0 then do this, but we have not mentioned what will happen if load is 1. So, the meaning is if load is 1, the value of T should not change, which means the value of T must be stored in a latch. Okay. So, in case of this kind of incomplete if then else statement, if you have, that will also generate a latch for some of the variables. Okay. This one example illustrates that. We shall be looking at some more examples later also. So, with this we come to the end of this lecture, where we have looked at again some of the Verilog constructs, and we shall be continuing with the discussion. There are a lot of other things to discuss also. We have looked at the different ways of assigning some values to variables. One is using the assign statement, another is equal to the equal to statement, another is less than equal to. So, what are the differences between these? Assign you have already seen, but what are the other two? So, we shall be seeing this in our next lectures. Thank you.